The night sky is a time machine. The further we look out into the universe, the further back in time we reach. What we see in the night sky is only a small percentage of the contents of the universe. Most is dark matter and dark energy. We know it exists, but its nature eludes us for the moment. No longer hampered by a hazy, often polluted atmosphere, telescopes and other sensors have been able to obtain clearer images from orbit thanks to advances in technology and engineering. In the 1960s, satellites began to explore the cosmos surrounding us. They saw beyond visible light into ultraviolet, infrared, X-ray and even gamma rays. Like the universe itself, our understanding of its beginnings, construction, evolution and future is evolving and constantly expanding. In the last 2 decades of the 20th century, the United States and other nations began to develop more substantial research programs, utilizing larger and more complex space-based telescopes.
For hundreds of years, thousands of years, humans have thought the universe is a very static place. If you go out at night and look into the night sky, you will see that things don't really change much. The universe appeared very static for a long time. We now know this is not true. The universe is a highly dynamic place, and things are happening all the time. Every single second, a star explodes in a gigantic supernova explosion somewhere in the universe. And we have to go and find it. We have to build instruments that are capable of finding those unforeseen events.
The Cosmic Background Explorer, or COBE satellite, started crystallizing the big picture of the universe by mapping the microwave background radiation left over from the early universe. Its successor, WMAP, created the most detailed portrait of the infant universe.
Well, because it takes the light over 13 billion years to reach us, we are seeing now what the universe looked like then, over 13 billion years ago. So it's a fossil remnant of what the early universe was like. And just like fossils are used to study the past, we use this light to study what the universe was like way back near the very beginning.
And you can see in there blue spots and red spots. And what those correspond to are slightly hotter and colder images of the sky. That's a picture there, those hot and cold spots, that pattern is really it's the afterglow of the Big Bang. On a sort of deeper long-term time level, it's this amazing consistency that the picture we can put together of the universe is relatively simple, that the pieces fit together. It's a stunning confirmation of the study of cosmology for many years now. It's just built up, and here it is. In some ways, we're getting to know the cosmos like we know our own backyards.
ESA's Planck spacecraft joined the fleet and expanded on their observations. Together, they were able to map vast regions in multiple wavelengths, enabling astronomers to determine the size, shape, and age of the known universe.
Just 370,000 years after the universe began in a Big Bang, all that existed was a hot plasma similar to a candle flame. Protons and electrons, seen as the red and green balls, were bouncing around, scattering the light. The particles of light, called photons, shown in blue, couldn't go far without colliding with an electron. As the universe cooled, the protons and electrons could pair up, forming hydrogen atoms, and the light was free to travel. It's been traveling freely ever since, through the dark ages before there were stars, then past the formation of the first stars. As the universe expanded, photons lost energy, changing color. They went past clusters of galaxies. The path of the photon is slightly bent by the gravity of the clusters. Now and then, going through a cluster, an electron, that green ball, would collide with some of the photons. They would change their path, past more matter, more little wiggles due to gravity and mass. The photons traveled for 13.8 billion years before they reached the Planck detectors and died a glorious death, giving up the information that they had gleaned passing through the entire universe to our instruments and enabling us to make this beautiful map of the universe.
The various satellite telescopes have sensors designed for use in multiple wavelengths of the electromagnetic spectrum, from near to far infrared light, through visible and ultraviolet frequencies, to X-ray, gamma, and cosmic ray detectors. Each can reveal unique aspects of the construction of stars, nebulae, galaxies, and the exotic blazars and black holes. However, in the public's eye, the poster pin-up star of the latest generation would undoubtedly be the Hubble Space Telescope. Over its 25-year lifespan, Hubble has produced some of the most amazing imagery of the cosmos as it delves back in time through visible and infrared light. Another advantage of Hubble is its long lifespan, thanks to several maintenance missions, which allows it to study objects over a long period of time with some amazing results. Newborn stars eject streams of matter into the surrounding star-forming region. Known as Herbig-Haro objects, these supersonic jets can be seen to change over a very short time span.
If you see just a single picture from Hubble, you can interpret it in many different ways. But the fact that Hubble has been around for as long as it has been means by taking multiple images, you can actually stitch them together and watch how the material moves. And so that really gives you the only way to get true insight into the physics of the dynamics of what's going on.
The Horsehead Nebula in the Orion constellation, silhouetted by glowing gas, is a good example. Infrared can see right through, revealing its dark secrets. The Spitzer telescope is one of NASA's great observatories.
Spitzer is an infrared telescope, which means it sees through the dust that's out in space. And by seeing through the dust, we get to pinpoint the stellar nurseries that are out there where stars are being born.
We've been flying for about 10 years. That's about 3,600 days. We have 5,000 published papers. That means every day a new paper based on Spitzer data announcing new results and new discoveries is published, which to me is absolutely amazing.
Spitzer has made several surprising revelations within our solar system and beyond. It helped pinpoint some of the most distant galaxies in the universe, and Spitzer's ultra-high-resolution map of the Milky Way substantially improved our understanding of our own galaxy's structure. Japan and ESA had launched their own infrared telescopes in various infrared wavelengths. The European Herschel, in particular, focused on massive star formation regions.
We are really happy to have new things and to understand, trying to understand, because we are making a new step towards our understanding of massive star formation. So the idea is that Herschel can reveal this population of highly embedded stars that are formed in gas and dust cocoon, but that are not visible at optical wavelength, for example. So we need Herschel to detect all this population of very young stars.
The next great spaceborne infrared telescope is the James Webb Telescope, which is nearing test completion in preparation for its launch in 2018. It will have a 6.5-meter primary mirror, almost 3 times larger than Hubble. However, ground-based telescopes are also working in the infrared spectrum.
So there's a large complementarity between space and ground, from space with the Hubble images, you can characterize the images, you see the images much better. With the ground-based telescopes, you then can take that light and look at spectra and then find the redshifts, for example, for distant galaxies, or you can take infrared observations, which Hubble couldn't do for a long time, to then see how these objects look in the infrared.
Together, they have delved into the star-forming nebulae left over from exploding supernova and witnessed the birth of stars. Another observational tool in the electromagnetic spectrum for astronomers and cosmologists is the X-ray band.
An amazing discovery of the last 20 years is that every galaxy, like our own Milky Way, has a massive black hole at its heart. And as material from this galaxy, dust and gas, falls onto this central black hole, it radiates, and we can see that. So if we look at the sky in visible light, we see stars. If we look at the sky in X-rays, we see black holes.
You can observe X-rays from very distant objects. So you can investigate the cosmic structure of the universe. So you investigate the matter distribution in the universe via observing the galaxies, the black holes in the center of the galaxies to very far distances, and this is very important for cosmology and to learn about the origin and the evolution of our universe.
X-rays are absorbed in our atmosphere, so X-ray detectors must be placed at either high altitudes by balloon or into orbit. NASA's flagship X-ray telescope and one of their great observatories is Chandra.
If you want to find black holes, you want to use an X-ray telescope.
What we're tending to find is that a cluster of galaxies has a bright central galaxy in the middle. It's often an active galaxy or a quasar, so a supermassive black hole in the middle of a big galaxy. Because when the cluster is forming, a lot of the material tends to fall to the middle, so you get the biggest galaxy in the middle.
So you see the power of an observatory, an observatory like Chandra with a state-of-the-art telescope and these imaging and spectroscopic capabilities of its science instruments can do things that maybe weren't even things that you planned on doing because you didn't know about them at the time. And a lot of the science with Chandra falls in that category.
The most recent telescope launched is NuSTAR, which has the ability to focus X-rays for a much sharper image. One of NuSTAR's main scientific goals is to make a full census of black holes in the universe. X-rays have also revealed the explosive processes of nova seen only at these wavelengths. ESA have their XMM Newton studying cosmic evolution, and Integral, the International Gamma Ray Astrophysics Laboratory, looking at gamma ray frequencies, revealing unseen structures and new sources of gamma rays.
So Integral is important because it's one of the few satellites which look in gamma rays. And together with other satellites and observatories around the Earth, you can get a complete picture of how these stars evolve. And without Integral, you're missing a large piece of the puzzle. We want to know how did they produce the elements which we are made of. And these are the objects which throw all the different kinds of material into the universe, and they wander off into space. And we are made of all these elements which are produced by the supernova. So it is important for us to know where does life originate and how does it originate.
Gamma rays are at the top of the electromagnetic spectrum, the most energetic and powerful photons which stream from black holes, exploding stars, and even from our own star, the Sun. Originally called GLAST, the Fermi Gamma Ray Space Telescope observes the entire sky in high-energy gamma rays every 3 hours, creating the most detailed map of the universe ever known at these energies. When it detects a new gamma ray burst, it works in conjunction with the SWIFT satellite. Then Swift is able to spin rapidly across the sky and point an X-ray telescope and an optical ultraviolet telescope at the possible location of the gamma-ray burst.
BLAST is primarily devoted to seeing in a new energy range.
It's designed to pick up at the upper end of the Swift energy range and carry it on up to much higher energies.
And it allows you to just see, stranger and more exotic things the further up in energy that you go.
BLAST and Swift are very different. Swift is like a nimble small satellite that points here and there, but it isn't surveying the whole sky, it's pointing in its particular objects. BLAST looks in the high energy gamma ray sky, and looks over the whole sky at all times.
So when we see something interesting with BLAST, we can ask Swift to go look at it with their other telescopes and gain additional information about it.
We don't know what will happen over the next 10 years, hoping that Swift will still give us exciting data. But what we do know is that Swift will give us exciting new data because of its pure nature. This is what it was built for, to study new, unforeseen, unexpected events. And they will inevitably happen.
There is one more type of radiation being studied in orbit: cosmic rays. The 8-ton cosmic ray particle detector, called the Alpha Magnetic Spectrometer or AMS instrument, is attached to the International Space Station. Cosmic rays consist of protons, alpha particles, atomic nuclei of heavier elements, electrons, their antimatter partner positrons, and gamma rays. Studying these particles may answer some fundamental questions, like the unexplained absence of antimatter and the nature of dark matter in the universe.
Calibration of positron is important because when you have dark matter collision with another dark matter, you produce excess positrons. So the characteristics of the excess positron tells you what's the origin of dark matter.
About 80% of the matter in the universe is invisible to telescopes. This dark matter neither reflects, absorbs, nor emits light, yet it interacts with matter via a gravitational influence which can be seen in the orbital speeds of stars around galaxies and in the motions of clusters of galaxies. Yet, despite decades of effort, no one knows what this dark matter really is. This visualization shows galaxies composed of gas, stars, and dark matter colliding and forming filaments in the large-scale universe, providing a view of the cosmic web. It is believed that dark matter provides the framework for this web. Galaxy clusters are the largest gravitationally bound structures in the universe. It is also believed that after the Big Bang, the universe originally decelerated in its expansion, but then changed gears and began to accelerate.
Important discoveries in astronomy and astrophysics was the discovery of dark energy, and that is that the universe is accelerating apart. What people are trying to do using various different techniques, and again in all the different wavelength bands, is to measure the parameters to characterize the dark energy.
With a launch date set for 2020, ESA is building Euclid, a space telescope which, it is hoped, will chart dark matter and dark energy's effect on the universe.
I'm working on Euclid. That is a mission to map the universe. And for that we built a highly precise telescope in which we can map dark matter structures as well as derive the properties of the dark energy.
Understanding dark energy will allow us to understand the future of the universe.
The interesting thing is we get more and more dark energy. Why? Because our universe is expanding. And with our expanding universe, we get more dark energy in our universe. Now, the ordinary matter, so dark matter and normal matter, is not expanding, it's diluting. So the fraction of dark energy compared to normal matter is increasing in time. When the universe expands more and more, we get more volume of our universe, we get more space, and we get more dark energy.
The leading particle physics model for dark matter is called weakly interacting massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays is kind of like two bullets hitting head-on in a crossfire. It's very rare. But when you go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher in this detection with a gamma ray telescope.
In his theoretical process, Schnittmann's computer simulation shows particles of dark matter around a massive spinning black hole. All of the action takes place close to the black hole's event horizon, the boundary beyond which nothing can escape, in a flattened region called the ergosphere. Within the ergosphere, the black hole's rotation drags space-time along with it, and everything is forced to move in the same direction at nearly the speed of light. Concentrated, fast-moving dark matter particles collide and make gamma rays, but only some of this high-energy light can escape the black hole, in this case from the left side, where the black hole is spinning towards us, giving us a lopsided glow of high-powered gamma rays. The simulation tells astronomers that there is an astrophysically interesting signal they may be able to detect as gamma ray telescopes improve. Schnittmann believes this would be conclusive evidence of the WIMP model.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.
Future missions will see a gravitational wave observatory to study gravity waves and test Einstein's theory of general relativity. The Athena mission, mapping hot gas structures and searching for supermassive black holes, due to launch in 2028. The Sloan Digital Sky Survey, the most ambitious astronomical survey ever undertaken, will provide a three-dimensional map of about 1 million galaxies and quasars. The recently refurbished and upscaled CERN Large Hadron Collider is one of the tools in search of WIMPs and other exotic particles that may help explain the fabric of the cosmos. Then perhaps the scientists, astronomers and engineers can turn their attention to other mysterious theories brought about by particle physics, such as multiple dimensions, entire universes beyond our own, and what lies beyond the event horizon. These in time will become the new frontier.